Welcome. We have here Philippe Schwaller from EPFL, who's been doing a lot of cool work at the intersection of chemistry and machine learning, and trying to develop, accelerate our ability to do chemistry using machine learning. Welcome, Philippe.
Thank you very much for the nice introduction. It's a great pleasure to be here today. So most of you don't know me. I grew up in Switzerland, went to EPFL for my undergrad. Then after a short experimental work at Empire Materials Research Institute, I joined IBM Research, and that's where I stayed for roughly 5 years, starting a PhD at the University of Cambridge and finishing it at the University of Bern. And since 2022, I'm back at EPFL. So kind of a bit closing the loop. And the other thing that you can get from that slide is that I had amazing mentors all along the way. And closing the loop is very much related to my mission statement of accelerating discoveries in chemistry with digital chemistry. And if something worked well during the 2.5 first years of my tenure track, it was really the hiring. We have a super diverse group with lots of brilliant talents, and it's a great pleasure to work with all of them. So yeah, let's start with chemistry. You probably all know that we have a nearly endless chemical space to explore. If we just take the number of drug-like molecules, the estimated number is often stated to be 10 to the power of 60. And my group is focusing on using machine learning to accelerate the molecule and materials design cycle. Really, from what kind of molecule do we want to make? What properties could those virtual molecules have? Always trying to push towards experimental validation. But this is kind of not done very often in machine learning, and it's also it's super slow, and this is because the make part is quite challenging, and so a big part of my group also focuses on how to make molecules, how to synthesize materials, going from synthesis planning to reaction optimization in both more chemistry and sometimes also a bit of material science. And today I will we will look at large language models for chemistry as well as small language models for de novo design. But let me first start with chemical reaction. As you see here on the screen, if we have a data set of chemical reactions, we can imagine different tasks where machine learning could help us. For example, a forward reaction prediction, where based on the precursors, you try to predict the most likely product, or you can turn it the other way around and basically for new molecule that might not have been synthesized before, and ask what kind of reactants, what kind of precursor mixture would I need to kind of get to that molecule. What is more challenging is the multi-step synthesis planning task, where you kind of go from this target material to commercially available building blocks. In any case, if you tackle something with machine learning, you need some data. And in chemistry, we have on one side the literature, which is very broad, also contains quite exotic reactions and so on. But the sad part there is that it's typically not very accessible. Then we have more and more groups that are collecting their reactions in electronic lab notebooks and could make them available. Or we had also recently more and more publications with high throughput experimentation data sets. What is kind of cool there is that it's really higher quality data, and if something has been done under the same condition in a robotic platform, typically those reactions are more robust. Then we have simulations that also help us to add additional information, but typically they also have to be tuned to a very specific reaction, so cover a narrow space. And we have the patents, the US patents, for example, from Google, and there we know it's not the best quality of data in the patents, but there are lots of mistakes or like kind of small things that are not 100% correct. But we can imagine that whatever we train and whatever we can demonstrate on patent data that is super noisy would only become better if we had higher quality data available. So I wouldn't be here today and talk to you if there had not been Daniel Lowe and Roger Sale text mining the US patents back almost like 10 years ago and basically extracting millions of reaction equations and procedures. And one way to represent chemical reaction equation are reaction smiles. And here you have the corresponding 2D depiction. So for the next 40-ish minutes, we'll kind of focus on those text-based representations of chemicals. And here, just to show you, the SMILES representation has been introduced back in the 80s. And I'm sorry for the pointer, I should change that. But kind of, you can follow the string and see how like the atoms, the C and C, and then you have for the branching, you have the brackets, and then for the ring openings and closings, you have the numbers. And this gives like a way how to represent molecules as text. Smiles
So
are not unique.
question,
Yeah.
this looks like a tree embedding. You embed a tree into the graph, and that's what you're documenting here. Is that right?
Yeah. Yes, it's something like that. Yeah, it's basically, yeah. And
And, and how do you
then
know
what you
when the cycle
maybe,
comes back?
hmm?
So how do you know when the
Sorry,
tree comes back and makes a cycle? Is that documented here?
if you, I didn't fully understand the
So I
question,
see
sorry.
that you see the branching point is a parentheses, and you can do any hierarchy that way.
Yeah.
But where that branching point comes back to an earlier part of the tree, how would you know that?
If you, okay, you have the, I think like what you are referring to are the ring openings and closings.
Exactly.
Here you basically have the one that opens a first ring and it's closed back with the second one. And
It's a
this
pointer.
two, two is like connecting with two. Yeah, those are pointers to the,
Got it. That makes a lot of sense. Thank you.
yeah. So you also see it here, maybe quite nicely. Yeah. So this oxygen atom is here with the two, is at this place here connected back to the carbon atom with the other two. Hope that's, yeah. And the cool thing with SMILES is that it basically allows you to represent atoms as letters, molecules as words, and then we can just tokenize them and create those sequences of atoms and borrow methods from human languages to apply them to chemistry. What sounds super obvious today, like back in 2016, 2017, when we started working with those language models on chemical reactions, this was kind of orthogonal to what the field was doing. And yeah, in the meantime, like clearly the transformer architecture by Google is kind of the go-to architecture, and similarly to how you train like kind of machine translation, you can also model a chemical reaction prediction task where you kind of want to translate from precursors to the most likely product as yeah, as a task for transformer models. And back in 2018-19, when we presented that, like without integrating any rules, just by training on hundred thousands of reactions, you could get accurate predictions with this molecular transformer, and it will work much better than rule-based approaches and graph-based approaches that might be more fitting to molecules. And this was actually like the first use case of a transformer model in chemistry. In the meantime, there are plenty of other approaches, but like what is kind of striking is that all the better performing approaches on those standard benchmark data sets still use the transformer architecture somewhere, either with the graph encoder and then with transformer decoder, or they are like kind of very similar architectures to the molecular transformer with more data augmentation or extensive pre-training. So kind of very much aligned with what happened in NLP. Another thing besides like kind of reaction prediction that my lab is super interested in is retrosynthesis. And there you kind of want to go from a target molecule to commercially available building blocks. And you want to do that step by step, going backwards until you kind of know the complete route to this target molecule. And there have been plenty of approaches in the last decade, like the people around Chematica, they were like kind of hand encoding a lot of expert rules that they found in papers. Then there was the Nature paper by Marvin Segler, where based on the atom mapping, basically like could automatically extract the kind of reaction rules, and which then like led to a lot of open source work that was like kind of reproducing and extending this approach. Also from uh, for example, AstraZeneca, but also from the people around ASCOS at MIT. We went kind of another way, not encoding rules, but learning them. And we introduced a molecular transformer retrosynthetic model to do one-step predictions backwards to like try to predict as diverse sets of molecules as possible that could lead to the same target molecule. And because we couldn't kind of evaluate all the reactions manually to get the best suited synthesis paths, we use the forward prediction model with a fixed target to get scores to find the more likely routes to present to the user. What we kind of did differently than like all those template-based models or what was commonly done in the literature is that we try to predict as much information as possible in one go, and include not only reactants that contribute atoms to the product, but also like catalysts, solvents, bases, whatever you want in the same string, which makes the whole kind of single step prediction quite harder, but gives you enough information that you can then go on. And what we had in mind was RoboRxN. It was during COVID time, so imagine chemists at home doing the creative process of designing a molecule, then connecting to the cloud where they get access to the synthesis planning tool. But if you look at that, such a reaction equation is not enough to kind of go into the lab and just perform that chemical reaction. So what we added on top, again, based on a sequence-to-sequence transformer, was model that from an arbitrary chemical reaction would predict like kind of a recipe to do with structured actions to then be able to perform that in the lab. Or back then we were working on this RoboRxN platform, and that's why we could also execute some of those syntheses on the robotic platform. And there I just want to highlight Theo Lino and the whole team, because I was mostly working on the machine learning models and far away from the hardware. This, I don't know if you hear this, but this robotic platform actually exists, and from like collaboration. It's more prototype, but it works. Yeah, one of the crucial models to get that is really the slice to action models uh, developed mainly by Alain Rocher, who is now at Google, so Google Zurich. And yeah, the kind of cool thing here is that it's the first time where we actually tried to introduce in the prediction reaction conditions like temperature and time. They could still be modified by the human expert, but at least you would get the first guess of how long a specific reaction could take and at what temperature it could be run. Yeah. everything that kind of I've shown you so far is really like super small scale compared to today's world. Roughly up to 20 million parameters trained on a consumer GPU for from like 4 years ago within like 2 days. So lots of iteration possible, and with kind of this trend going from single modalities where we kind of translated a set of smiles to another smile, or the vice versa, then combining multiple modalities. So going from the reaction equation in smiles to like structured actions. And what we see more and more recently, like I think like since 2022, is to use like general purpose large language models applied to chemistry. And one of the first works that where we fine-tuned that like a GPT model on chemical tasks was with Kevin Jablonka. Was recently published at some point this year after multiple rounds of reviews in Nature Machine Intelligence. And there are also some similar works on the open models. This like this Darwin family developed in Australia, and what I will focus on in the next few slides is really like kind of how can we make use of large language models in combination with like chemistry tools. And this is like kind of an approach that was taken by a few group by mine, but also this clarify from Alanas Burgosek at the University of Toronto, and co-scientist, which was published in Nature by Gabe Gomez at CMU. So yeah, to do that, we will go from encoder decoder models to encoder only models. And I think like kind of this to that audience, I can basically skip that slide. But what we kind of had in mind is we saw that in chemistry we have a lot of super useful tools in cheminformatics, quantum chemistry, and so on, but they all somehow live a bit in isolation. And depending on the tool, it can be super hard to set up. And it will maybe take me a few days from the GitHub repo until I would have a running code for my use case. But if we look at experimental chemists that kind of could maybe benefit the most from those tools, it's almost impossible, and this is not a time investment taken. On the other side, yeah, what we kind of wanted is to bridge the gap a bit between computational chemistry and experimental chemistry. At the same time, we saw that GPT-4, which was kind of the most recent model back then, was still very bad at chemistry. I think if we look at the O1 model now, it's a bit better, but still kind of as soon as you push those models outside what they have seen during training, they would typically just confidently hallucinate. On the other side, we had plenty of chemistry tools that lived in isolation. So we came up with ChemCrow, and ChemCrow Crow because it can use crows can use tools quite well. So what tools for ChemCrow? We included some molecule tools, like kind of to convert molecules or get different properties. Then general tools like a literature search, web search, code interpreter. Even the human expert became a tool. Reaction tools that are kind of referring to what I was presenting in the first part before I cut off, and safety tools. And given those tools, we could now kind of ChemCrow can now, instead of just giving a direct answer like a language model, think about the task, select the most fitting tool, generate an input, and get back some more precise information, loop around until it had like enough information to give us a final answer. And if we take an example in automated synthesis, then you can think of plan and execute the synthesis of an insect repellent, where like the language model would first think, okay, what is an insect repellent? Query either the literature or the web to get common insect repellents, get back DEET or a few other options, but those are names that do not contain any structural information. So it needed to kind of get that from somewhere. So it used the name to smice tool to get back the smice and the molecular graph, which wasn't then compatible with plenty of other tools, and it could use the reaction planner together with the smice to get a recipe. And because we had connected it to RoboRxN, we could basically in 2 hours show that we had synthesized DEET, or Chemcro had synthesized DEET. And this here is like one of the first demonstrations of like prompt to over different like kind of information to the execution on the robotic platform. We had a few other use cases in organocatalysis that were very similar, where we kind of prompted the Chemcro to find an organocatalyst and suggest a synthesis for the robotic platform. We could also, yeah.
Uh, I mean, initially you said this was the goal to be generic in the sense you have many GitHub repos that do chemistry and you can just use them. How difficult is it to deal with all the different libraries out there, or is that not feasible right now?
You mean as a single human to just
No, no, no.
deal with?
For Chemcro,
Or like
right now it
no,
seems like you have a fixed set of libraries you're using, and you presumably explain them to Chemcro. Is that fair?
yes, exactly. Yeah. So here we kind of did the kind of almost simplest approach of like connecting to plenty of APIs that were available, or like kind of just sometimes encoding a function based on a toolkit that would provide useful information to tackle some of those use cases. So this was, I would say, making use mostly of already available stuff and combining that with a language model to make it solve some chemical tasks. Yeah.
Okay.
But yeah, I think like kind of now of yeah, I guess like libraries are constantly developing, and I
Yeah.
guess you would need and language models are changing and so on. So you would have a lot of effort to keep this always up to date and working together. And no, but yeah.
Then how do you know if you're right? Is there a role for fine tuning based on successes, failures, that kind of stuff?
Here it's all just whatever we showed here is really in context learning and just prompt engineering, I would say, and not any fine tuning on good or bad campaigns. What was kind of fascinating to see is that one advantage that those language models have is that they can react to unexpected situations. So one cool thing was that the robotic platform had a validator, and when there was kind of an obvious mistake in the synthesis procedure, it would get back a log with kind of pointing to the error. So what was a typical example? Okay, one thing that happened is that the synthesis procedure had predicted the solvent, had the solvent amount that was too little to be able to stir the solution in that particular reactor. So it would get back that this information in the log, and the language model could automatically just update the synthesis procedure, increase that amount, and then against validate it against the robotic platform, and then move on. So this was kind of cool to see.
It makes a lot of sense. Like, I guess it's with code synthesis. And then
Yeah.
last thing, is there any? Can you blow up the robot? Just the bluntest way of asking it.
No, I don't think so. No, like the quantities are super little,
Okay,
and
that helps.
uh, yeah, no, that's yeah, and they're kind of. We also integrated some safety tools and so on. So more to that in a few slides.
Okay.
Um, yeah, you could also give like project similar to what maybe you would give to a kind of an intern or something like that. Hey, here's a nice data set of chromophores, clean that data, filter for particular solvent of interest, train a machine learning model on this data, and suggest me a molecule out of kind of selection of molecules that we can currently synthesize with a maximum absorption wavelength of 369. And Chemcode could do that, like use the Python interpreter to analyze the data, filter for solvent, train a random forest model, predict the property on this set of possible molecules, get back a retrosynthetic route, and final answer what molecule to go for. And then we found, we synthesized that molecule, and the maximum absorption wavelength was within the error of the random forest model that Chemco had trained. We also integrated some safety tools, like they're useful in kind of two different ways, I would say. Whenever you work with chemicals, you need to query for safety information, and you can just connect to those information sources, and Chemco could kind of give you those information directly. And on the other side, if you would like query for a controlled chemical, it would catch that and kind of have a small guardrail to prevent dual use. Here's an interface that one of my students programmed, and you see how it's thinking, generating the action input, selecting the action, generating the action input, and going on. I think like Chemco is really a proof of concept, and it's pretty modular. Like tool sets and LLMs can be changed, and back then only GPT-4 was like following instructions well enough. But today you would probably have plenty of other options of large language models. So yeah, should you always use LLMs? I think it depends. Like there are lots of like specific tasks where like you can train small models and they almost work perfectly on those data sets, and while large language models that are adapted from general purpose large language models have a really hard time to get good predictions. So we're not there yet, I would say. Also, automated synthesis is not solved because on one side you have like a lot of engineering challenges with the robotics, but on the other hand you have kind of you cannot synthesize anything for which you don't have the building blocks available at that particular point in the robotic platform. And I would say that the synthesis planning models are not always outputting very strategic routes. Even like how they are benchmarked, it's typically you have like a target molecule and you check whether the leaves are all commercially available. But this doesn't take into account like strategy, and you see a lot of examples where reactive groups are like kept over several reaction steps, and this would just be a slightly more strategic and complete synthesis plan for the same molecule. And in any case, whenever I talk to my friends in organic chemistry, what they would be more excited about is the complexity of vitamin B12 or other natural products. So, like, I have a team working in at EPFL that is trying to push the boundaries of what synthesis planning models can do. Yeah, we're not aiming for vitamin B12, but at least like a bit more complex molecules. And then once you have like kind of the reactions, typically you have to optimize them. Yeah, and kind of there's a lot of cool work also from the Doyle group about Bayesian optimization for chemical synthesis or chemical reactions. What we see in a lot of those works and is that quantum chemistry descriptors from DFT, for example, are sold as the best descriptors, but one-hot encodings perform often very similar. And then the question is it worth the extra like time to get DFT descriptors? And Bojana Rankovic from my team is working a lot with Bayesian optimization for chemical reactions. We have some work done where we try to move beyond one hot encoding and pick a problem where like kind of the one hot encoding becomes unfeasible because there's one category that has just too many entries. And recently also better last year at NeurIPS, we presented some work on using large language model embeddings for chemical reactions and directly going kind of from the synthesis procedure to the embedding vector and doing Bayesian optimization with that.
So let me actually understand what the options are. The DFT, that would be like the three-dimensional shape of the molecule?
It would no typically like kind of it's much more than that, and it requires a lot of human expertise because you would kind of relax your molecule, then compute for specific atoms that you know that are important for that particular reaction. You would compute specific properties of those atoms and kind of or combinations of atoms, and it's the thing is, if you change the reaction, you typically have to redevelop a pipeline to compute local descriptors again, like atomic descriptors again. So well, you can do that, and probably you have a slight improvement in such a low data regime. I don't think it makes too much of a difference compared to like simpler descriptors that you can just calculate easily for any molecule without having to look at which atoms are the most important ones. And yeah.
Okay, so then, I mean, our options are one hot of a smile string.
Yeah.
And the LLM is it's smiles embeddings or a different, like, what are you embedding with the LLM?
With the LLM, like kind of we tried a few things, but we kind of try to, because you can have conditions, you can have smiles, you can have like what we really tried is to be as close as possible to the original like reaction procedure and just to make it work with as many procedures as possible. So just go from like the text describing the chemical reaction to an embedding, and then we really don't need to, if this works, like we don't need any kind of we can just tackle nearly any problem in chemistry and have our pipeline behind that works on those embeddings.
Interesting. And one thing you haven't mentioned is I'm thinking now AlphaFold, like a molecular dynamics simulation, but the embedding from that, which would be kind of the embeddings that AlphaFold was apply to a particular molecular string.
Uh, I didn't really get the
Well,
connection with.
so what I noticed is you have a smile string, and
Yeah.
that's relatively one hot. And you have DFT, which is it's molecular dynamics essentially, but kind of maybe refined and focused because DFT is even more detailed than MD. And description of the text, embedding of the text description of the reaction. But one thing that I've not heard is MD, but embedded, which would be the AlphaFold embedding, like something like that, of the state of the molecule midway through the MD simulation.
Yeah. Okay. Yeah. You could, I guess, do something like that, but kind of it will probably take you a lot of time to for new reactions set up an MD simulation
Right.
that accurately like simulates that reaction. And what do you do? Kind of in chemistry, we often have like a guess what is happening, but the only things that you can actually observe is kind of your reaction setup and the procedure,
Mhm.
and you can easily observe the end result. And what is happening in between is kind of yeah, they are guesses, but and for like I guess well-known reactions, you almost certainly know what is happening, but there are other reactions where you it's really hard to tell how the transition state will look like and so on, and if there are maybe two competing reactions and what exactly is happening. So yeah, it's
I
not
understand
super
that.
easy to set up the simulation.
So let me poke on that. If you have you either have a simulation, great, you can run it. If you have an AlphaFold kind of thing, you have a bunch of input-output examples. They, roughly speaking, make a simulation. So I guess what are possibilities for inferring or specifying the dynamics, the internal dynamics that must be going on that are invisible?
What are the possibilities for inferring the
Yeah.
in, hmm, I think like kind of yeah, I guess like you okay, if you really want to know what is going on, then probably with an MD simulation or something like that, or like figuring out the transition state and then kind of calculating the reaction barriers and comparing, like kind of like that, you can probably get more accurate descriptions of what yeah, kind of a mechanistic explanation of what you actually observe in your experiments, but really setting up a simulation that captures everything, you need to know a lot beforehand.
Like initial conditions, that kind of thing.
Yeah,
Hmm.
that and you need kind of, because you can have kind of effects from the solvent from yeah, you have to, in a catalyzed reaction, you have kind of to figure out how kind of your reactant binds to the catalyst, and then and you need to figure out which is on of all those small steps, like which is the rate limiting step that is actually determining how your reaction proceeds and so on. So it's kind of, I think like, yeah, it takes some work to properly set up such a simulation, I would say.
That makes sense. Yeah, thank you.
Yeah. For the last few minutes, and I don't even know like what time. Okay, yeah, I will quickly also talk a bit about the design part, and they're kind of I would say we have two main flavors that we see in de novo molecule design. On one side, we have distribution learning, where okay, we start, if we want to design drugs, then we would start with a related data set like Campbell, pre-train a model, pre-train a generator, so it learns how to generate a molecule. And then if we do distribution learning, we typically know a few examples of molecules that inhibit the target, and then we fine tune the model on that, and we sample from that model to get similar molecules. What my lab is more interested in is kind of goal-directed learning. That's not about like learning the distribution of a small focused training set, but more like pushing the model towards generating molecules with a particular property profile. So you sample a molecule, then you score them, and I think this is the most crucial step. And based on that, you update through reinforcement learning your model. And What we are really interested in, and maybe this relates again like to your last point about simulations, for one single molecule, it's much easier to simulate compared to a chemical reaction, I would say. And what we would like to have are kind of oracles that can be a computational prediction or simulation that mimic that correlate the best with like the real world, the experimental observation. And if we have sample efficient models that can learn from a few simulations, then we can go to more and more expensive simulations that are closer to reality. And if you kind of imagine that the cheapest that you could have as scoring function would be a machine learning model. But because here we're really trying to push out of distribution towards like something that has a property profile that was not yet observed, they're typically really inaccurate because they work well in distribution, but pretty bad out of distribution. So what you would typically see is kind of scoring functions there for drug discovery that are using molecular docking or like XTB or DFT, single point DFT for materials there and catalyst design. But you can push that to MD simulations, which are typically more expensive, can be like hours or days. And but if you had generative models that are sample efficient enough, you could optimize your the molecular generation against such simulations. And for that, we're working on different approaches, and specifically like Jeff Gore from a lab uh, did kind of developed augmented memory where we kind of try to make maximum use of all the data that we see during the optimization tasks. And back then, at least when we published this work, we were like leading the PMO benchmark that was published in Europe's 2022. And the cool thing there is kind of that they fixed a limit to the number of calls to the oracle that you can do to optimize the molecules. And but it's kind of surprising. If you do that, you have augmented memory that at least back then topped it. You have reinvent, which is also an LSTM based technique, which augmented memory is based, but with some additional tracks that we have integrated that performs super well. And you have a lot of really cool big machine learning conference papers that are super beautiful. I think when you look at the techniques they are developing, but not sample efficient at all. And yeah, it's kind of there, like small LSTMs still work the best. More recently, we decoupled augmented memory from reinvent and developed Saturn, which is our framework for sample efficient de novo design. I think one of the main changes is that, okay, we went from LSTMs first to transform models, which in that case didn't give us any improvement, but we found that state space models like Mamba would make the generation a lot more sample efficient. And in some like multi-objective docking optimization tasks with a very restricted Oracle budget of 1,000 calls, we could show that Saturn was able to find some hits above a certain reward threshold, and the diversity a bit suffers a little bit, but we are kind of much faster finding like the first molecules about specific threshold, and also finding more molecules. What is
So
super interesting, yeah.
just to understand the setting here, you're assuming you're going to have an oracle, such as one of these simulations, and your goal is to call the oracle the fewest number of times,
Yeah.
while like with the goal of discovering a molecule or designing a molecule with best properties.
Exactly. Yeah. In that case, the optimization was on the docking score that kind of where you have a protein target and you want to bind a molecule in a pocket, and you want to have the best docking score as possible. Then you also don't want the molecule to become too large, and you want to maximize the drug likeliness, and you want to do all that with a limited budget and find molecules that are above a reward threshold of zero point 0.8, and for different targets that you see on the left, there are more challenging targets and easier targets, but we can show that the Mamba-based approach yields a lot of molecules above a given reward threshold, and also uses less oracle calls to like find the first molecule or the first 10 molecules in what we call oracle burden.
So
Yeah.
question, if you were to relax, it's not number of Oracle calls, but the amount of compute time you can use. So you can have more cheap calls and fewer expensive calls. How does this change?
I think like this is, yeah, no, that's a totally valid question, and this is something we are exploring. I think like it would definitely make sense, because here we're still like optimizing towards a docking simulation, which is super cheap. So it's just to show that we could like find valuable molecules with a very restricted number of oracle calls, but with the thinking that if this works here, we could basically go to more expensive simulations and still find molecules now with a more accurate simulation and still limited oracle calls. And if you were to do that, the only thing that would make sense is that first to take the cheap method that you can run almost for free to already like maybe bias the model a little bit into the right space, and then optimize for the cheaper, no, for the more expensive simulation, I wanted to say.
Can
But
you So can
yeah.
you use this technique to also train your cheap surrogate? I mean, effectively, how do you train your cheap surrogate? You do a bunch of Oracle calls in
the,
those spaces that are relevant, and then from that data set, you train your surrogate.
No, okay. So this would be like predictive models, but docking is a simulation. So this is not trained at all. This is physics-based, but not super accurate. And then you can go to more and more computationally costly physics-based methods that should give you more accurate values about the binding.
Good. So now what I'm
So
asking about is training a cheap surrogate using the simulations, but still with obviously a limited budget of simulation runs because they're still expensive.
yeah, yeah, no, yeah. I think this could work. Then if you're generating something drastically new, you're never kind of sure that the cheap surrogate will still be able to predict accurately. I don't know, like
Yeah.
if you're kind of like the you will at maybe let's take that picture here, and because this is like kind of cool thing we found in the optimization approach, like what we could observe is that Mama had kind of a super particular behavior. It would always within like an epoch kind of explore locally and then push towards like more valuable, more rewarding molecules and explore that space again locally, and then push again further. And if you now imagine that you would have trained a cheap surrogate model on the epoch 1 and 2, I don't think that you would have predicted any of the better rewarding molecules later on. You would have just assigned similar values to 1 and 2 to those molecules, even with the cheap surrogate. While with the simulation, it captures those changes and gives you better rewards.
Okay, so where I'm leading to is this technique seems to, it's a sample efficient choice of runs. If I were
Yeah.
to run 100 of these, or maybe say a large number of these design tasks, and use your technique to generate these simulation runs that are in the correct region of the dynamic space,
Yeah.
the circuit trained on that should be generic, I would hope, for that entire region of this, I don't know, dynamic space, right? That you can keep using, like, to find similar design tasks. Or
If
is
you
it
have
too?
similar design, but this would like kind of, if you go from one protein to another
Mhm.
protein target, then you're kind of outside.
It's still too
Then
far.
you, and
Okay.
yeah, you're kind of out of distribution again. So yeah, no, but it. I'm sure, like in if you redo the same experiment all over again, you could probably reuse like the previous rounds to kind of inform your model. That's, I guess, a valid thing. Yes.
Yeah,
Yeah.
I'm
Yeah.
thinking
Yeah.
I'm running a cloud service. Like, imagine this is fully grown up and productionized. You have 1,000 chemists all doing their stuff and doing their runs, and I can throw away my simulation runs, or I can make a targeted neural surrogate that is for the community, based on the community.
Definitely. Yeah. Yeah.
Would that be usable, or is it just a bunch of point runs that are just don't generalize?
I don't know, like kind of they could be usable if it's done in a good way, I guess.
Hmm.
And yeah, no, there are plenty of ideas floating around about like creating synthetic simulation data and using that to have better starting points and things like that. So kind of yeah, I guess this is definitely a valid thing to do. Yeah.
Got it. Thank you.
I will not. I will try to be fast on the last because we're
Oh
already
yeah, sure.
past the hour. But you can go further because one of the biggest bottlenecks is synthesizability because you won't have a real world impact if you cannot synthesize that molecule in the end. And there are plenty of kind of works in the last 2 years that focus on synthesizability, constraint generation, where typically they start from building blocks and then they generate the molecules by making them react together and so on and stuff like that. And but how they measure synthesizability is typically against a retrosynthetic tool and often against the AI Zinc finder from AstraZeneca. And what we just thought is instead of kind of constraining the synthesis like that, why not add the final scoring like this AI Zen finder retrosynthetic tool directly in our scoring function? Because if this is the goal, then the only reason why people are not doing that is that their model is probably not sample efficient enough to learn what a synthesizable molecule is. And we could kind of show that again with super restricted Oracle budgets, 1,000 calls on a optimizing for four different objectives at the same time within the time frame of 2 hours. We could have like almost 80 to 90% of the molecules generated that are deemed synthesizable according to a Zen finder and have kind of reasonable properties. So this made us tackle the next problem because like kind of what you want to do in a few cases is kind of to kind of enforce specific building blocks. Imagine your lab has already made a complex molecule and wants to have the best kind of the best possible like binder from that particular starting point, or you're kind of interested in waste materials and you kind of you want to start from waste materials and synthesize some interesting molecules. So we kind of thought about can we enforce building blocks in the routes on top of whatever we optimize. But this is kind of the challenge there is that you kind of have a super sparse reward, but because even if you have like 50 like enforced building blocks, finding one of them out of like 3 million building blocks that will be possible, stuff like that, over several route steps is almost impossible. So what we had to come up with is a new reward function that we call Tango. And it takes two to tango because it's a combination of Tanimoto similarity and the substructure match. And like that, we were able to actually like enforce specific building blocks in the synthesis route to then get to high value molecules. And we can do this with starting materials constraints, but also like imagine you already have a hit, you can synthesize that specific molecule in the middle, then you could do late stage diversification and say how could I modify that molecule with a few reactions to have even improved properties. In the end, just the last thing I want to show is FS score, which was just published in chemistry methods, and there it's again tackling this this bottleneck of the synthesizability, but from a different aspect, assuming that chemists all have a different view on synthesizability. One molecule that you give to one chemist and is synthesizable for that chemist might not be synthesizable for another chemist. So we did kind of a pre-training on like general chemical reactions to a bit have a ranking what is more synthesizable than kind of reactants are more synthesizable than products, inspired by SC score by Conocoli. Then with limited pairs of two molecules and labeling which one is more synthesizable, you can then show on diverse cases that we can actually have a good synthesizability score. And because we are kind of human experts are not always available, if we want to combine that in a reinforcement learning loop, then we can replace the human expert with like a make on demand library and basically say whenever we generate a molecule, we will generate one of those pairs with the closest make on demand molecule that we find, and like that we can bias the model to generate up to like in this case we had roughly 40% commercially available molecules without requiring human labeling, and this works a lot better than some other scores that are typically used. If you're interested in that, there's a recent review on that topic that we have written, and while everything else was mostly about large and small language models, it was commented at some point on LinkedIn that that we kind of reconstructed the timeline and did an immense amount of work that modern LLM agents would not have been able to complete. Yeah. With this, I hope I could show you the potential of language models, transformer, state space models, and so on for chemistry. With ChemCraw, we had kind of one of those first showcases of autonomously solving some generic tasks in chemistry. The evaluation was super challenging, so this I could have talked about that, but we were working on ChemBench, which is kind of a large benchmark data set for language model evaluation. If you're interested in de novo design, then we have Saturn, our framework, and FS score to adapt for your synthesizability score. And yeah, with this, let me just highlight all the people and the funding. I'm really thankful about that I'm allowed to work on all those cool projects at EPFL, and thank you very much for your attention.
Yeah, thank you very much. Let me ask two maybe application questions. One would be things like, have you considered things like biochar? What I have in mind is everything you've done is chemical formulas, but there's a bunch of things like biochar, which 3D structure, like porosity, the matrix thing becomes a rather important output of the chemical reaction. So how does that complicate it?
Okay, so we tackled this two ways, I would say. What I've not shown here today is like kind of I would say invasion optimization. We have some kind of work that hopefully will soon go at least on archive, and that where we kind of try to optimize for specific shapes of a particular nanocrystal, because the shape is very much related to the catalytic properties. And but there we're kind of there, it's more like going from synthesis procedure directly to kind of the macroscopic properties of those catalysts. Um, in all the cases with when in de novo molecular design, the 3D structure comes in the simulation. We are basically incorporating like 3D information in the reward function, but we found that for the moment, and this is an open question, and but at least like kind of my people are believing that 2D generation coupled with 3D reward function is more efficient than trying to do 3D generation and working on the 3D space directly. And but I think this is debatable. You have plenty of different opinions, and but so far we have quite a lot of success working on this 2.5D representation, and starting from that. Once you go to chemical reactions, I think like it gets much more complicated, because you have not just one single molecular entity. You have multiple reactants, you have catalysts, solvents, everything that is kind of all in 3D space that yeah, you somehow have to simulate well if you want to have any benefit from 3D information.
Right. Okay, makes sense. And then the other one is things like bioplastics. I asked that
Yeah.
one because unlike most chemical synthesis, the feedstock is highly heterogeneous, but you're supposed to, from any odd garbage, you have to still create the same thing. How does that
Mhm.
complicate it? And to what extent can we absorb a variety of bio feedstocks to create a uniform product?
I think this is I guess we have some approaches internally that could potentially move towards that. Yeah, I have some I don't know how much I can share openly at the moment, but
Okay.
like kind of I think like by going in this direction of enforcing building blocks that kind of waste materials, and
Mhm.
pushing a bit in this direction, yeah, there are some thing we can do. I'm not saying we're gonna solve the whole thing, but like at least those are the steps required to work towards such a vision, I would say. Yeah.
All right. Excellent. Well, yeah, thank you very much. Thank you for joining us.
Okay. Hi. Thanks a lot, and